All right, so let us finish the last lecture with a few remarks. We have introduced those equivalence classes based on a space of what we call physical states. It's a physical space where all states are annihilated by the A of S annihilation operator, and we have defined the subspace of that, which is the space which defines equivalence classes, which are all the states which have the form A dagger of S acting onto something physical. And then we define the quotient space between the two, which is then the physical Hilbert space. And we want to investigate the properties of this physical Hilbert space. And what we have already seen last time was that you can define a scalar product on that space of equivalence classes. And of course the definition is the obvious one. You take a representative of each equivalence class and define the scalar product between equivalence classes as the value of the scalar product from representatives. But this makes only sense if the scalar product does not depend on which representative you choose. And it's independent of the representative, and that was the last remark from the last lecture. And that means that you can define a scalar product on this space H physical. Now a next property is that this space H physical contains only states with positive norm. And that is the result of explicit inspection, because we have looked at the explicit one-particle states. And by looking at them explicitly, only the states with polarization 1 and 2, they are members of this physical Hilbert space. They have positive norm. And so similarly, you can do the same analysis for the multi-particle states, and then by explicitly looking at the elements, you see this property. And then, of course, you have a scalar product, which has positive definite norm only, and so the space defined in this way is really a Hilbert space in the proper mathematical meaning of the word. Then the third property is the following. Let us now look at Poincaré transformations. U dagger of lambda A acting on a creation operator U of lambda A. Okay, and then let us look first at the creation operator for these scalar polarizations. What is the result if you do a Poincaré transformation of the scalar polarization? We have already investigated this. And the result was some factor times another A dagger of S operator. So A dagger only goes, A of S only goes into itself under Poincaré transformations. And that means that this space Vs, which is defined by A dagger acting on something under Poincaré, goes into itself. So all states in this space under Poincaré remain in the same space. That is the outcome of that. And if you look at S or 1 or 2 polarizations here instead of S, then you know that the result also only contains polarizations 1, 2 or S on the right hand side of the Poincaré transformation. And that tells us that states in this physical space, they also remain physical under Poincaré transformations. So those two spaces are invariant under Poincaré transformations. Poincaré transformations do not lead out of those spaces. And then it tells you what happens with Poincaré transformations on the physical Hilbert space. If you take an equivalence class, then you can apply a Poincaré transformation onto one representative of the equivalence class. That representative is physical, under Poincaré, it remains physical. If you take any other member of the same equivalence class, it differs from the first one by Vs. Vs stays Vs under Poincaré. That means the Poincaré transformed state is also equivalent to the Poincaré transformed state of the first representative. Therefore, an equivalence class has a unique, unambiguous Poincaré transformation. That means you can define those Poincaré transformations also for an equivalence class, and the result is well defined, and so that means you have now translated your unitary representation of Poincaré on the full space. You inherit a unitary representation of Poincaré on the space H physical of the physical positive definite states. U of lambda A unambiguously defined on this physical Hilbert space, and so we have now really defined a unitary representation of the Poincaré group on our Hilbert space of physical states. And so we have a scalar product, positive definiteness, unitary representation of Poincaré, and taken together, that really means that we have now a fully consistent quantum theory of spin 1 massless particles. So that is therefore the end of the discussion. We have reached a very beautiful goal, namely the theory is constructed. As usually, we needed to construct the Hilbert space of states. That construction was now very involved. We needed to construct a unitary representation of Poincaré. We have done it, and we have analyzed the elements of that space which contains the transverse polarized spin 1 or helicity plus minus 1 massless particles, and so everything that we would like to fulfill is fulfilled. That is the result. And now let me just end the whole thing with a few remarks. Or are there first any questions to this? Yes.
Yeah, a conceptual question. If I say that the physical Hilbert space is the B physical quotient with Vs, but for example, my A dagger 1 under a Poincaré transformation mixed with S.
Mm-hmm.
Why do I say that these are physical if I have this component of S in the Poincaré transformation?
Yeah, that is this tricky thing. Under Poincaré, the original representative, lambda equal 1, goes, let's say, into a linear combination of 1, 2, and S. The linear combination will always contain a non-zero component of 1 and 2, but it will also maybe contain a non-zero coefficient in front of the S. And then you say, okay, this coefficient in front of the S is, you can go to a different representative of the same equivalence class where you make this S vanish. That is the point here. So any state which has this form, let's say a dagger of 1 plus let's say epsilon times a dagger of S, this is equivalent to the same state which contains only the a dagger of 1. That is exactly the meaning of saying that this Vs defines our space of equivalence classes. That's exactly the point. And so that is what makes the whole approach Lorentz covariant. You need the S in order to have a Lorentz covariant field operator which transforms like this. In order to have that property, we need this relationship that A1 goes into A of S, that we saw explicitly, that is necessary, and the coefficient turns out to be something specific coming from the Lorentz transformations of the epsilon polarization vectors. Okay, so that is needed, but then we now say this is equivalent to that state. It's in two different representatives of an equivalence class, and then we have managed to achieve two things. On the one hand, Lorentz covariance, but on the other hand, we only describe physical degrees of freedom with the correct properties.
Yes, I have a different question. The limit space of physical states is defined as the quotient space of the physical states and some ES. But I remember from a mathematics lecture that we defined a quotient space as some space divided by some equivalence relation, and not divided by a space, where it's the set of all equivalence classes with respect to that equivalence relation. But now we divide by a space instead of an equivalence relation. How does that definition relate to this way of writing?
I don't know how else one would write it, but the meaning is most likely exactly the same, because our equivalence relation is of course defined by saying that two states are equivalent if they differ by an element of Vs. So that's exactly the same definition of the quotient space. What is important is, which is not visible in the way of writing, Vs is a subspace of the physical space, so this equivalence statement is also well defined. So you have two different elements of this. They might differ by an element of that subspace, and then they are called equivalent. So this is the same definition as the one you know in mathematics. Maybe the notation is a little bit different, but this notation is actually really the common notation in the context of at least gauge theories in this formalism. But one might use different notations as well. But the meaning is certainly the one that you know. Or do you see some contradiction in the meaning? No. Right. And yeah, so, and I mean, maybe it's not bad to have this visualization, because after all this complicated mess that we have done, the simple thing is really this. If you have a state which has this creation operator, it means just the same as that state. And so if you have some coefficient here, x times that, it's equivalent to that state. That's just a simple picture. I wanted to say this at the end, but let me say it now. It's relevant for the exercise sheet as well. Namely, since you ask about notation, so the notation is quite common, as I just said. And in particular, it's very common in this form, which you see on the exercise sheet, because in this Kubo-Ojima formalism, which is the counterpart of Gupta-Bloiler for non-abelian gauge theories, you have an operator QB, and this operator happens to satisfy the following equation, namely the operator square is 0. Operator square is the 0 operator. And then you can define the physical space as the space of states which are annihilated by this QB, and that is analogous to our definition. In our case, the physical states were annihilated by A of S. So QB is similar to A of S in that sense. And you can interpret this as saying that psi is gauge invariant. Very loosely speaking, okay, it's just to have this analogy, very loose analogy. Then you would say that QB is a generalization of gauge transformations, but on the space of quantum states. And so if you have QB acting on something is 0, it sort of means that this state is kind of gauge invariant state. Okay? And so then all the states annihilated by QB are called physical. And then you define that space Vs as the states which have the form that they are written, psi can be written as QB acting on some other state. So, right, QB acting on some other state. So it's a total variation under this QB. And so you could interpret this by saying that this psi is a total gauge transformation. Is a gauge transformation and hence unphysical. So this is a loose interpretation of this definition. So you have gauge invariant states and unphysical states which can be written as a gauge transformation of something else. And because this QB square is 0, it's clear that this Vs is now also a subspace of that V physical. Because whenever a state is a QB transformation of some other state, if you act on it with another QB, you get QB square and you get 0. Therefore, this Vs is a subspace of the physical space. And that is the same structure as in the Gupta-Bloiler case, only the structure is a little bit more elegant because you have just one single operator which automatically appears in both places in the same way, and because of this QB square property, automatically and manifestly one space is a subspace of the other one. And then you can also say that the physical space is, let's say, the kernel of the operator QB, and that space is the image of the operator QB. And then in that language you can say the physical space is defined as this thing, the kernel of the operator divided by the image of the operator. And then you have a nice mathematically looking definition of your physical Hilbert space. And you see that this is a direct generalization of what we have here in the abelian case, but this structure fully works in all gauge theories, including the most complicated non-abelian gauge theories. And so this is also a motivation behind the exercise that you should do. And because you can re-express our current formalism also in this way. Okay, but now let me make a few other remarks which are also important, I think. Let me first give you an outlook on interactions. So we will now make manifest a few remarks that have been done already before. So let us now imagine how an interaction term could look like. An interaction can be written in terms of an interaction Lagrangian. And let us simply make the ansatz A mu times J mu, which would be the correct ansatz for electromagnetism. If you derive from this the Maxwell equation, then you get really the proper Maxwell equations with currents and sources. And in our context, that could be also some combination of other field operators, maybe electron field or proton field operator, whatever. But we do not analyze the content of this J mu, but we simply make this ansatz here. And then the question is, when is our interaction ansatz consistent? We have now this complicated Gupta-Bloiler structure with physical subspaces, quotient spaces, and so on. And then one requirement that we should make in this context is that the interaction is defined consistent with our quotient space structure. What does that mean? It means exactly the same as what we have just required from Poincaré transformations. If you have a Poincaré transformation, the Poincaré transformation should be consistently defined for each equivalence class. That means it doesn't matter which representative you choose, you always end up in the same equivalence class. And the same thing should be required from the interactions. That means we require that the following object, which would be the d4x integral of this interaction Lagrangian density, if you act on it on some physical space, then, okay, this is also, I didn't explain it yet, then you should end up in the physical space. So if you start with a physical state and you let the interactions do their job, then you still end up with a physical space, and the interactions do not lead out of the space of physical states, because that would ruin our interpretation of the theory. And similarly, what I just said in words is, if you start out with a state which is in this VS state, so different members of the same equivalence class, then you should end up also in the space VS. That means whatever representative of an equivalence class you choose to start out from, you always end up in the same equivalence class after doing the interactions. So if that is the case, V physical is mapped into V physical, VS is mapped into VS, then the interactions are defined consistently with our quotient space structure. That is the requirement that you must impose in order to have a reasonable interpretation of your interactions. And what is the mathematical implication of this requirement? So basically, all of this is equivalent to requiring that a decker of S commutator with those interactions, that should be 0. Because if that is 0, then all the definitions of physical states and equivalence classes remain unchanged under the interactions. So if you first start out with a state which is annihilated by A of S, then after the interactions it's still annihilated because the commutator vanishes. And if you have a state which is a decker acting on something, it remains a state with a decker acting on something because the commutator vanishes. So that is really the technical requirement that you need to impose if you want to have consistent interactions on our space of equivalence classes. And now we need to evaluate a decker of S, let's say a concrete P comma S, with first of all our field operator A mu of X. And what is the result of that commutator? I think we did have similar commutators already on Tuesday. And so now you must imagine that this is of course this typical integral and the sum. And here you have epsilons, you have a's, you have e to the minus ipx, and the complex conjugate of that. And then which of the commutators are non-zero in our basis 1 to ls. In our basis 1 to ls, there was only one commutator which is non-vanishing, and this is the one where the A dagger of S hits the A of L. This commutator is non-zero. A of S with A of S, that was 0, but A of S with A of L, that was non-zero. Okay, so this indefinite metric thing. And so therefore you get something from here, and what you get, the commutator between A dagger and A of L, gives minus 1/2 times the usual coefficients because of the definition of A of S and A of L as linear combinations between the other ones with normal commutation relations. And so therefore you get minus 1/2 times the usual result, and the usual result would be this epsilon mu of P comma L here, and then e to the minus ipx. That's the result. And so now, what is actually the value of this result? So the epsilon mu for longitudinal polarization is of course the momentum P mu divided by the energy P0. And so therefore we can again write the whole thing as a derivative d mu acting on something. On what it acts is actually not important, but let's say it acts on minus 1/2 and P0 in the denominator times e to the minus ipx, and then we should multiply with minus I. No, plus I. So now it fits. So that is the result. And so therefore, the commutator between our A dagger and the photon field operator gives us a total d mu derivative. What happens if we plug in this result into the previous expression? So the commutator A of P comma S with this object, that is now the following. It's an integral d4x, you get j mu, and from the commutator with A, you get d mu of some function. Let's call it d mu of f of x, but this function is not really important, but it's some function. And so we can do partial integration, and then you get d4x with minus d mu j mu times f of x. And so therefore, lo and behold, what you see is that the commutator of your interaction term with a dagger of S gives rise to d mu of the current that you couple your field to. And what we wanted and what we actually needed was that this commutator vanishes. If that commutator vanishes, then the interactions are compatible with our quotient space structure. So now, under which condition does our commutator vanish? It vanishes under the condition that the current is conserved. D mu J mu equals 0. So we get as a requirement that we need to couple our massless spin 1 particle to a conserved current as opposed to a non-conserved current. That is the important physical outcome.
طبعا هذا يتفق مع ما ذهبت إليه من أهمية هذه البولاريزيشن اللي هو ال بولاريزيشن، لأنه يعني يعطينا الانتراكشنز أو الكوميوتيشن وذ انتراكشنز لاجرانج. طبعا يعطينا زيرو كما ذكرت في الفيديو السابق أن الزيرو هو نسبي، بالتالي هذا الكوميوتيشن هو يعطينا زيرو بالنسبة للأبعاد، لكن في الأبعاد الأخرى لا يعطينا زيرو، إنما يعطينا هذا الكرنت، هذا التيار. وهذا التيار طبعا ذكرنا أنه محفوظ في الأبعاد الكبيرة، لكن في الأبعاد الصغيرة ليس محفوظا، وإنما يتضخم من وسط التفاعل وأنت خارج التفاعل. يتم تضخم هذا التيار لأننا نتحرك من وسط كثيف الطاقة إلى وسط خفيف الطاقة أو قليل الطاقة، فإنه يتضخم بذلك. يعني هذا الأمر يعطينا تفاصيل أكثر، وعلينا مراجعة والتدقيق في هذه المسألة تحديدا، هذا النوع من الاستقطاب.
So, if d mu j mu equals 0, in other words, we have current conservation, then this integral over the Lagrangian density is compatible with the quotient space structure. That means you can consistently define the interaction really on the space H physical, and it has a well-defined meaning. Can be defined on H physical. Without ruining the interpretation. So that means consistent interactions for a massless spin 1 particle are only those where the massless particle couples to a conserved current. And that is a highly non-trivial result, which is observed in nature, because the spin 1 particles that we know, like the photon, they indeed do couple to conserved currents, like the conserved electromagnetic current in the Maxwell equations. And you can view this as an outcome of the quantum field theory analysis of the quantum theory of massless spin 1 particles. So that is a nice result. And let me make a second small remark. How much time do we have? Okay. Okay, then let me continue with a few more remarks. And the next remark is actually on an alternative approach. So right. So let us change gears. Instead of discussing now further the covariant case, where we have modified the Lagrangian by a gauge fixing term, and then we obtained negative norm states and needed to discuss this quotient space structure, we will now do the alternative. Namely, we use a particular gauge, the so-called Coulomb gauge, which is a physical gauge. In this gauge, only the physical lambda equal 1, 2 degrees of freedom appear. There are no negative norm states at all, but on the other hand, Lorentz covariance is lost. So we already saw the two options 2 days ago in our general analysis, and now we focus on this second option, at least as a brief set of remarks. So you can find more about this also in Weinberg's textbook in section 5.9. He only uses this approach. So let me just sketch what happens. You quantize the original gauge invariant Lagrangian directly, but under the external constraint of the Coulomb gauge, which is nabla A equals 0. And since we are dealing with free fields without interactions, we in addition also have A0 also equal to 0. Let me highlight, in general, Coulomb gauge is always this, and that is a consequence of what is the interaction. If you have no interaction, that is 0. If you have interactions, that is something else. And this is always Coulomb gauge. Or alternatively, like Weinberg does it, start directly with the quantum theory of the lambda equal 1 and 2 polarizations. So we have in our Hilbert space immediately those states which we already discussed on Monday, which are the physical states. We have explicitly shown that those describe helicity plus minus 1 massless states, and therefore those are really the physical states of a physical spin 1 photon, for example. And you could simply say, as we have at one point also said, let's just take the Hilbert space composed out of those states and throw away everything else. And that is what Weinberg does. And in both cases, whether you start with a quantization of the Lagrangian under this constraint, or whether you start with a quantum theory of those polarizations, anyway, you end up with a field operator A mu hat of x, which has this form, where you have now only the polarizations lambda equal 1 and 2, and otherwise it has the usual structure. That we have already seen. And so here the point is that we have no L or S polarizations, but only lambda equal 1 and 2. And okay, so we have essentially already said what is the outcome of this, and so let me just write it down coherently once more. The Fock space consists only of physical states. They have positive norm, and they have the correct interpretation as massless spin 1 particles. And so in comparison to the Gupta-Bloiler formalism, it tells us that the Fock space which results from this procedure contains always one element of each equivalence class in the other formalism. One element of each equivalence class of the H physical Hilbert space of the other formalism. So on that space you can define the Poincaré representation as before. And as a result, of course, you know that you get the correct transformation properties of the lambda equal 1 and 2 states. But we also get this law, let me just abbreviate it, U dagger A U is equal to lambda mu nu times A nu plus D nu omega with this additional term. So the Poincaré transformation of the field operator is not covariant. That is the problem of this formalism. So the formalism is very physical.
أنا أعتقد في هذا الموضوع بالذات أننا هذا يعني كونه أن يكون الفوتون non covariant هذا في حد ذاته امتياز وهبه الله سبحانه وتعالى لنا. لماذا؟ بهذه الآلية أو هذه الخاصية يمكن الفوتون أن يعبر بين الفضاء الحقيقي للتفاعل والفضاء الذي نحن فيه ويحمل معلومات. هذه المعلومات دقيقة جدا وهذه المعلومات هي متصلة، يعني هي تعتبر متصلة، وبالتالي نستطيع أن نأخذ هذه المعلومات الدقيقة جدا جدا ويعني نحرك بها اكتشافات كثيرة. وربما هذه الخاصية التي جعلت الفوتون يكون موجودا منذ بداية خلق الكون إلى الآن، مثل الخلفية الإشعاعية وما إلى ذلك، ربما يكون بهذه الخاصية الغريبة جدا. ولاحظ أن الكوفاريانت هذه تتعلق بالنسبية الخاصة، النسبية العامة، تتعلق بالجرافيتيشن والكيلوفيتشر بتاع للفضاء وعلاقته بالطاقة أو بالكتلة. إذا الفوتون لديه خاصية غريبة جدا، هي أنه مليء بالمعلومات الناتجة من فضاءات المختلفة، سواء كان فضاء نحن أو فضاء التفاعلات أو فضاء بداية الكون أو أي فضاء آخر. فهذه ليست مسبب في الفوتون، إنما هي بريفليج بالنسبة للفوتون ومفترض أن نستفيد منها. كما رأينا أن الاستقطاب للفوتون أو الاستقطاب زاوية الاستقطاب تخبرنا الكثير عن الكتلة، وهذا ما سندرسه في الانتراكشنز إن شاء الله تعالى، أنه سندرس زوايا الاستقطاب ويعني وزوايا حركة الجسيمات بين الشعاع الساقط والشعاع المنعكس بالنسبة للجسيمات ذات نفسها. فالضوء يعطينا معلومات جميلة جدا جدا بموجب هذه الخاصية أنه حساس جدا للكوفاريانت، يعني ممكن اعتباره هو نون كوفاريانت، نون لورنز كوفاريانت. وهذا الحد الغريب الذي يضاف إلى الفوتون بحيث أنه نجعله ننقص الديجريز اوف فريدم له. هذا الحد الغريب هو الذي يعمل المعلومات، وهو الذي يجعل الفوتون مثل الجاذبية ومثل النسبية العامة، أو يحمل خصائص النسبية العامة. فهذه خاصية جميلة جدا جديرة بالبحث.
Very nice to interpret up to this point where you see that the field operator that you have in this formalism just does not covariantly transform under Poincare. So that is of course the result of explicitly breaking manifest covariance by the gauge fixing condition. We have now the same problem but just in a different guise from before. We need to ask ourselves what happens if we want to introduce interactions. So again, we make the ansatz that the interaction Lagrangian is given by A mu coupled to some current J mu, whatever it might be. And now again we should look at our theory and ask, is there anything that we should require for our interactions for them to be consistent? And now there is no quotient space, so there is no problem related to that. But there is a problem related to Lorentz invariance. The question is, are our interactions Lorentz invariant? They look Lorentz invariant, but they might not be, because this is actually not a 4-vector. It's not a 4-vector operator. It does not correctly Lorentz transform as a 4-vector. Therefore, this object here, let's assume that that would be a 4-vector, then it's really not obvious that the whole product is Lorentz invariant, even though it's written like it would be Lorentz invariant, but it's not. So we should require something extra in order to get Lorentz invariance. So in this case, our requirement should be that U dagger of lambda A acting on such a d4x L int integral U of lambda A, that this should be Lorentz invariant. So that should be the same as, let's say, the original d4x L int integral. So it should just be a Lorentz invariant interaction. So clearly saying that this J mu is a 4-vector, that is nice but not sufficient. But of course we require this anyway, but it's not sufficient. What could go wrong? What happens is that under this transformation we get an extra term which is not invariant, which comes from this derivative of omega, and so the extra term has the form integral d4x of d mu omega times J mu. And that is of course by partial integration the negative of omega times d mu J mu, and therefore, as you probably expected, we end up with the same requirement as before, namely the interaction is Lorentz invariant if the coupling is to a conserved current where d mu J mu is 0. So if d d mu j mu is 0, then the interaction is more current. Invariant. Okay, so it's the same conclusion, and therefore you see, regardless from which point of view you look at the whole situation, you can do whatever you want. Many options in doing the quantization, you will always encounter some obstacles and some problems. You can always solve them, but if you want to have interactions, you need interactions which couple the thing to a conserved current, and that is the outcome of the quantum field theory analysis of spin 1 particles. So since you said I can go on for the entire time, let me make yet another small remark, but there is a question. Yeah, no problem. Yes, it remains like this. It never changes. That is the final result for the A mu field operator. What do you mean by the propagation? The free field is fixed. It is fixed. By fixed, I mean the result is there. You can write it down and it will remain like this forever. That is the result. It is the result of the field operator in Coulomb gauge. This field operator satisfies this thing. It satisfies it on the operator level. It also satisfies that thing. A0 equals 0 on the operator level, and both are manifest in our choice for the epsilons, because now only the epsilon 1,2 appears, and the epsilon 1,2 had a 0 in the 0 component, and it was orthogonal to the spatial P. Therefore, both conditions are manifestly implemented in this choice of the field operator. So in that sense, it is a nice object. It completely fulfills our gauge conditions. And that is even better than with the Lorentz gauge for the other case, where we could not require that as an operator identity. But here we can require all of those conditions as operator conditions. And that is the positive statement about this field operator. And the other positive thing is that the creation and annihilation operators really directly correspond to physical states for a physical photon. And the only disadvantage is that small problem here. And that is just the thing that you have to accept. In both formalisms, you have to accept one evil. And here, that is the thing that you need to accept. And if you then go on to the interacting theory with a conserved current, then those extra terms drop out. And so in the end, you can say you can ignore them in terms like this. You can ignore them because they drop out. But that is then a consequence of the special choice of the interactions, which are then, of course, gauge invariant. So gauge invariance would be the symmetry that you can impose onto the Lagrangian to guarantee that this A mu always will couple to such conserved currents. But here we do not directly see gauge invariance, but we see the more physical thing, namely current conservation. So, other questions? So then I wanted to make actually a simpler remark, which also connects to the exercise sheet from this week. Namely, let us look again at probability amplitudes for processes. As I already mentioned, it will typically happen that a probability amplitude has the form like this. So we will have some Feynman diagrams. And the Feynman diagrams have an open index mu. And then there will be a factor from some epsilon which comes from the photon field operator. And if we have a physical polarization, lambda equal 1 or 2, then those are the epsilons for this lambda equal 2 for physical states. Okay, and then forgetting about all the details, but simply knowing or assuming that a probability amplitude will have a form like this, you can now ask yourself what happens with such a probability amplitude under a Lorentz transformation. If you do a Lorentz transformation, then let's simply say the mu goes to lambda mu nu times m nu. We don't know why that would happen, but I mean, let's just assume it will automatically happen as a property of all the remaining terms that appear in the Feynman diagram. They do the usual thing and transform in a Lorentz covariant way. But for the epsilon, for lambda equal 1, 2, we already know, and that is your exercise, that it will not transform into lambda mu nu times epsilon nu for lambda equal 1 or 2, but there is an extra term. There is an extra term which appears on the right-hand side after the Lorentz transformation, which is proportional to the momentum p mu. So in the other way of saying it, on the right-hand side there can appear also the epsilon L with a polarization L that can appear on the right-hand side too. Equivalently, there appears a term proportional to the momentum. So if you want that the probability amplitude is Lorentz invariant, then you should now again require something, namely this product of that Lorentz transformed M and the Lorentz transformed first line. That is of course indeed Lorentz invariant. But what might disturb the Lorentz invariance is this extra term here. So the whole thing would be Lorentz invariant. So it would be Lorentz invariance if we have the following condition, namely that this m mu times p mu gives 0. If that is 0, then clearly the second line here in the non-covariant Lorentz transformation of the epsilon drops out, and therefore the whole product m times epsilon behaves in a Lorentz invariant way. And so therefore this condition here would be a condition which basically would guarantee Lorentz invariance of all such matrix elements or probability amplitudes. And this, okay, let's just go on here. This is sometimes called what identity? For matrix elements. For massless spin-1 particles. And this what identity that a matrix element vanishes if you replace an epsilon by a p, that helps in establishing Lorentz invariance. And so also here, this is similar to current conservation, because if you do a Fourier transformation of that equation, then it goes into p mu times the Fourier transformed current gives 0. And so you see that this equation is similar to that one, where basically this m has the role of the current which couples to the photon. So in that way you can understand that that equation is similar to current conservation, but it's also a condition for Lorentz invariance. Yeah. No, okay, sorry. I mean, this is just some unknown coefficient which depends on the precise Lorentz transformation. Yes. That was my last remark. So now we could stop and turn to the exercise sheet. But you can also ask more questions. Are there any more questions? Yep. Can be done. That is a little bit difficult to see right now for us because we have not yet defined how the Feynman diagrams are related to field operators, but they are given in terms of some matrix elements of or expectation values of field operator products. And if you write them like this, then you can see a relationship between this and a direct appearance of this current as an operator. Indeed, yes, that's right. Other questions? All right, then let us stop here and turn to the exercise sheet.